Hello. Uh, Hello, everyone. My name is Taihan Chen. I'm from National University of Singapore, Department of Architecture, and my supervisor is Professor Chao. My research topic is the effect of tree plantings and street aspiration on the thermal environment using a urban canopy model, UT&C. First one is a simple background introduction. Street greenering is a very important adaptive strategy for UHI urban heat island effect and can provide the shading, provide the evapotranspiration, and also can increase the urban albedo, which is very important for the microclimate improvement. And some research also point out some adverse effects of the street greenering. For example, can cause the higher humidity, lower wind speed, and also worse thermal comfort and accumulation of the pollutant. If you also consider the urban morphology, so potential shading overlap of the building and trees also can affect the cooling performance of the trees. So that is very important. Appropriate greenery planting strategy are very important, especially for some high density cities like Singapore, like Hong Kong, these kind of cities. We have two research questions. So first one, we would like to evaluate the impacts of the greenery on the thermal environment. Second, we like to evaluate the impacts of the urban context or building typology on the greenery cooling effect. So that's two research questions. So methodology, there are three main modeling methods related to the greenery cooling. So compare with the first one and second one, and we select the urban canopy model as our tool. It has a very good advantage, for example, a quick calculation speed and also fully developed urban and vegetation energy model. So the model we select is called UT&C. It's an urban canopy model proposed by Dr. Naika. As you can see, can contain the radiation model, energy turbulence model, and also the heat fluxes model. And it's a quick and feasible and effective evaluation for designer. This is very important for the designer. And using is quite simple. If you need to input the data for background meteorological data, urban morphology data, and the output data will be the pedestrian parameter like air temperature, humidity, and also wind speed, and also can calculate the thermal comfort index. Before we use this model UT&C, we like to have a validation first. The validation we select is scale outdoor experiment. It's cost so much. I conducted this experiment 3 years ago, and we also published some paper in the Science of Total Environment. And generally, it's 2D concrete building models of about 1.2 meters, and the vegetation also is scale. And it's totally a controllable model under the real weather condition and have been verified well for the similarity problem. So we select so much experiment to validate and cross-compare the UT&C model. So I'd like to show you some vegetation validation result first. So the first one would be the pedestrian wind speed. So as you can see, the original model performance on the wind speed is not very well because as you can see, the wind speed cannot match very well with the measurement result and even report a wind speed increase that if you try to put more trees in the street, which is far from our understanding and also far from the physical law. So actually we do a modification of the wind model. We replace the wind model inside the street by a new semi-empirical model based on the drag coefficient and frontal area density of building and trees. Let's see the final result of our modification. So as you can see, the wind speed from the modified model shows great agreement with the major result, no matter in trees or no tree cases, and the statistical result also perform well for this model. And more importantly, I want to highlight that the wind model not only took part in the calculation of the wind speed, also took part in the turbulent energy exchange model for the whole model. So it's also very important to see the performance for other parameters. For example, the air temperature. So we also have a validation for the air temperature TA. As you can see, the TA also match quite well for the no tree cases or tree cases. We can see a slight overestimate for the tree cases at the midday, and compared with other model, this result is quite good for us. And the second one will be the relative humidity. So the relative humidity in without tree cases perform quite well, match quite well, and there is overestimation for the three cases uh, during the daytime. And the reason for the overestimation of RH could be the assumption of the model or the variability of physiological process of the plants or the trees. So as you can see also, you can compare with other model, they also capture similar overestimation of the RH. So I think for the urban canopy nodes, still very difficult for them to capture or reproduce the evapotranspiration process of the plant or the trees. So I think further investigations still require. So this is relative humidity. And we also calculate the thermal comfort and have a validation as a final index to compare. So thermal comfort is very important. We calculate the TMRT and also UTCI. And as you can see, TMRT performed very well in no tree cases or tree cases, which means that the model captured the shading situation and also a radiation process for the tree cases and no tree cases. And the UT&C perform also is good for from our result, but we can see a slight over estimation for the three cases, and this mainly due to the overestimation of RH because RH take part in the calculation of UTCI. So overall, this is our result of the validation. So we believe that this validation can be used to conduct our parametric study. So we conduct a parametric study. I'd like to show you some setting of the parametric study. So we like to see, we select two key single tree parameter, leaf area index, LAI, and tree radius R3. So in this situation, we fix the HW aspect ratio, which is a building parameter, as one, only one. We do not change HW, and we change LAI or R3 to see the individual effect of each single tree parameters. And second one, we like to see the coupling effect of building and tree. So we change the HW from 1 to 5 and also change the AOI or R3 to see the coupling effect of HW and AOI or the HW and R3. So I'd like to show you some result of the parametric study. First one would be the simple one, individual effect of R3. So the horizontal is the R3 increase. If you try to use larger tree crowns, means that you have stronger shading. So that means that you will have a lot of temperature decrease, no matter in air temperature, ground temperature, TMRT, UTCI, we have a enhanced cooling if you try to increase the R3. But for the LAI, the situation is different. I'd like to show you that if you only see the T ground, the ground temperature and TMRT, you will see a temperature decrease, which means that the larger AOAI actually can intercept more solar radiation. But for the air temperature, we can see a decrease and then increased chance. This is very interesting, and our explanation for that is caused by the tree crown temperature. So as you can see, the tree crown temperature also decreased first and increased, which means that when you use a too high LAI, although the tree crown also absorb a lot of solar radiation, but it also can be a heat sources which can affect the surrounding air, so lead to this kind of air temperatures situation. And as a balanced result, UTCI shows decrease first and be stable when you increase the LAI. Yeah, so this is two individual effect of LAI. And then I like to show the coupling effect. So this is one of the example I like to show you of the diagonal variation of UTCI. And the vertical axis is the HW. So if you try to increase the HW, the situation is that you can see a high temperature area narrow very significantly, and no matter in tree cases or no tree cases, which means that the increased HW decrease the temperature. But we also want to know the effect of HW on the cheese cooling performance. So we also calculate the difference between the tree cases and non-tree cases, and then we finally get this figure is the daily maximum reduction of UTCI. So it's delta UTCI. It means that the reduction of the UTCI maximum, and as you can see in this figure, every point means one cases. So we conduct about 250 cases to output this figure. And the blue points means that higher HW, and the red points means the lower HW. So we have three conclusions from this figure. So the first one is that if you compare the HW1 and HW5, we can see the cooling effect provided by tree could be significantly weakened. by the larger HW. So this is the shading of the building cause this kind of situation. And second one, if you look at the figure B, if you try to increase the R3, you can see if you increase the R3 in HW5, you cannot get further cooling. But if you increase the HW for HW1, you can get further cooling for UTCI. So our another result for that is increasing R3 can be less efficient at the narrow street canyon because it also caused by the shading overlap of the building and trees. And last one would be the LAI. If you try to increase LAI, no matter in HW1 or 5, you are gonna get further cooling for UTCI. So based on this figure, I would like to give some suggestions for the planner or designer. And the first one is LAI would be recommending 4.0 for both wide or narrow streets. But for the R3, we will recommend 5 meters for wide street and R3 for 3.4 meters for narrow street. Because if you try to increase the R3, you cannot get further in the narrow street. So this is our coupling effect result. We also output other parameter, but I cannot show today because so I'd like to show this is final result. So this is the conclusion, including our validation result and our modified model result, and also the individual effect of the tree planting, and also the coupling effect of the building and the trees. And last one is our suggestions for from this study. And the paper has been submitted as a journal paper, and this is all the result. And I'd like to thank uh, Dr. Naika Meli and also other co-authors from ETH and US and also SYSU. Thanks for your support. Yeah, okay. This is all my presentation. Thank you.
Thank you, Simone, for good timing. We have time for a couple of questions.